We will now discuss the solution of a problem from the section Linear Algebra, and this question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and the problem is related to the positive definite quadratic forms. The given question is, let capital A is equal to the matrix Aij be a real symmetric 3 by 3 matrix. Consider the quadratic form Q of x1, x2, x3 is equal to x transpose capital A x, where x is a column vector given as x1, x2, x3 transpose. Which of the following is true? We are given four options. Option 1, if Q of x1, x2, x3 is positive definite, then Aij is greater than 0 for all I not equal to j. Option 2, if Q of x1, x2, x3 is positive definite, then Aii greater than 0 for all I. Option 3, if Aij greater than 0 for all I not equal to j, then Q of x1, x2, x3 is positive definite. Option 4, if Aii greater than 0 for all I, then Q of x1, x2, x3 is positive definite. We are given capital A is a 3 by 3 real symmetric matrix, and we have the quadratic form Q of x1, x2, x3 defined as x transpose Ax is equal to, where x is the column vector given as x1, x2, x3 transpose. Then we have to discuss which one of the following four is true. We now discuss the solution of the problem in detail. We have capital A, whose ijth entry Aij is a real 3 by 3 symmetric matrix. That is, A is equal to the first row A11, A12, A13, second row A12, A22, A23 because it is symmetric. Aij is equal to Aji, and the third row is A13, A23, A33. So this is the entries are real numbers and it is a symmetric matrix. Agreed. We have the quadratic form Q of x1, x2, x3 is equal to x transpose Ax, where x is the column vector whose entries are x1, x2, x3. So that will be equal to x transpose will be the transpose of the column vector is the row vector x1, x2, x3 A into the column vector x2, x1, x2, x3. So this is the quadratic form associated with A. Agreed. We recall a definition. A quadratic form Q of x1, x2, x3, which is given as x transpose Ax, is said to be positive definite if x transpose Ax is positive for all non-zero column vectors x. For all non-zero vectors, column vectors x, x transpose Ax is greater than 0, is positive, then the quadratic form x transpose Ax is said to be positive definite. Agreed. Now, first we consider the statement that is given in option 2. That is, if Q is positive definite, then all its diagonal entries of A are positive. That is ai greater than 0 for all I. This is true. We will prove this one. Q of x1, x2, x3 is positive definite. And recall, then x transpose AX is positive for all x not equal to 0, for all non-zero column vectors. Agreed. Now, let E1 is equal to the column vector 1, 0, 0, or in other words 1, 0, 0 transpose. E2 is 0, 1, 0, the column vector. E3, 0, 0, 1, the column vector. And obviously these are non-zero column vectors. And x transpose AX is greater than 0 for all non-zero column vectors x. So these are non-zero column vectors. For them also it must be greater than 0. So replace x by E1. Now, in the place of x, you write E1 transpose A E1. Because it is non-zero, greater than 0, because it is positive definite. That implies E1 transpose is the row vector 1, 0, 0, the matrix A, into E1, the column vector. Multiply, and it is greater than 0 because it is positive definite. If you multiply, you will get only A11. Do it. A11 is after multiplication, you will get A11, which is greater than 0. Agreed. And similarly, E2 transpose AE2 is greater than 0 will imply A22 greater than 0, and E3 transpose AE3 greater than 0 will imply A33 greater than 0. So that's what is that we have proved. When Q is a positive definite quadratic form, then the diagonal entries of A are A11, A22, A33, they are all positive. They are all positive. So thus AII greater than 0 for all I, and the option 2 is true. So therefore the answer to this question is option 2, and the remaining are all not true. That I will show you, and in fact I have to stop here because the question is over. But I will show you how they are not true in the next slides. Agreed. We go to the next slide. So we go to the option 1. If Q of x1, x2, x3 is positive definite, then Aij greater than 0 for all I not equal to j. That means these entries Aij, when I not equal to j, they must be positive whenever it is a positive definite matrix. It is not so. To say so, I will give you a counterexample. So what is the counterexample I will give? A is equal to the 3 by 3 matrix, identity matrix I have taken. Agreed. Then the quadratic form corresponding to A is equal to I3, Q x1, x2, x3 is positive definite. Why? Because Q of x1, x2, x3 is x transpose AX. That is equal to x transpose means x1, x2, x3. A is the 3 by 3 identity matrix into x is column vector x1, x2, x3. Multiply, you will get x1 square plus x2 square plus x3 square. The sums of the squares is always positive. Whenever for all x not equal to 0, for all column vector x1, x2, x3, x1 square plus x2 square plus x3 square is always positive. Thus, x transpose AX is greater than 0 for all non-zero column vectors x. Therefore, it is a positive definite. Agreed. But in this, get into the matrix A, Aij, I not equal to j. That means A12, A13, A23. They are zeros. And if your statement given in option 1 is true, they must be positive, but they are not. Notice that Aij is not greater than 0 because they are equal to 0, not greater than 0 for all I not equal to j. So the conclusion of the statement, the statement given in option 1 is not true. Thus the option 1 is not true. So for this, the counter example A is equal to I3 will do. And for the options 3 and 4, we require another counter example. And we also recall a result on positive definiteness of the quadratic forms. A quadratic form Q, x1, x2, x3 associated with a real symmetric matrix A given by x transpose AX is positive definite. A is a real symmetric matrix. It is positive definite if and only if all the leading principal minors of A are strictly positive. All the leading principal minors of A are strictly positive. And now let us take let the matrix A, real symmetric matrix, is 1, 1, 1, 1, 1, 1, 1, 1, 1. All entries are 1. Now, what are the leading principal minors? You brush your knowledge on leading principal minors. And what are the leading principal minors in this case? 1. 1. Determinant 1 by 1. 1 is not mod. Determinant 1 by 1, whose entry is 1. 1, this one. And 2 leading principal minor is this one. 1, 1, 1, 1. Determinant, which is 0. And leading principal minor of order 3 is the whole of the determinant and is equal to 0. This is 0. Why? Because 2 rows are identical. This is 0 because 2 rows are identical. So what is that? We have observed that not all the leading principal minors of A are strictly positive. Not all the leading principal minors of A are strictly positive. So it's an if and only if statement. Therefore, it is not a positive definite quadratic form. Therefore, Q, x1, x2, x3, x transpose AX for this matrix A is not positive definite. This example is necessary for ruling out the options 3 and 4. Let's go. So we have this. For this matrix, the corresponding quadratic form is not positive definite. And let's take the option 3. If Aij greater than 0 for all I not equal to j, then Q of x1, x2, x3 is positive definite. Now get into A. Aij, A12 is positive. A13 is positive. A23 is positive. So Aij greater than 0 for all I not equal to j. But this quadratic form corresponding to this matrix is not positive definite. The conclusion, we have not arrived at this conclusion. So observe that Aij greater than 0 for all I not equal to j in A, but the corresponding quadratic form is not positive definite. Therefore, our option 3 is not true. And let's get into 4. If Aii greater than 0 for all I, then Q of x1, x2, x3 is positive definite. Now get into the same matrix A and see the diagonal entries are all positive, but the quadratic form associated with this matrix is not positive definite. So you are going against the option 3. So that means observe that Aii greater than 0 for all I in A, but the corresponding quadratic form corresponding to this matrix is not positive definite. Therefore, the option 4 is not true. So thus the options 1, 3 and 4 are not true, and therefore our answer is that option 2 is true. Option 2 is true. So that is the detailed discussion of the solution of the problem which is related to the positive definiteness of quadratic forms from the section Linear Algebra. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.